Oh, hello, guys. So if you can turn on your cameras, please. People are still joining, but I suppose let's begin. So we left with this statement or this question. Why does some information affect probability and other information does not? As we said, every information gives us some sense about the universe in which we find ourselves. And what we do here, we count the number of possible universes. So every information is relevant to that, but not every information affects probability. So let's take, this is what I mean, right? So probability is number of universes with a desired property, that's the probability E, divided by total number of universes. And because we divide, there are some situations where this ratio is not going to be affected by the extra information. So let's consider those two examples, guys. Calculate for two fair dice that are rolled, calculate the probability that first die is a 6. And B, calculate the same thing given that the sum is equal to 7. So we roll two dice, and I want sum equal to 7 for B. And I want the probability that 6 occurs. Thank you, Gustavo. So answer A and B, please write in the notes. Hopefully those are easy questions. All right, guys, thank you for messaging. Thank you for messaging. Now, here is what I wanted you to notice. I mean, all of you are correct, but be sure that it's not by accident. So how do you solve problem A? Properly speaking, the sample space are two outcomes, outcome on first die and outcome on the second die. There are altogether 36 possible universes. Is that clear? Just if the only thing on the universe is the outcome on those dice, if we have this restricted universe, then we have 36 outcomes. Now, the truth answer for question number A is 6 over 36. You agree? So there are 36 universes possible, and 6 of them are universes with a desired outcome. So you were all correct that the answer is 1 over 6, but it's more correct that the answer is 6 over 36. You understand? But what happened is that we cross the information out. It's incorrect to imagine that the second die was irrelevant. It just happens that we can scale both numerator and denominator by a factor of 6. And the answer for question B, when F happened, right? F does give us information on which universes we have. We no longer have, if the sum is 7, we no longer have 36 possible universes. We have exactly 6 possible universes, agreed? And only one of those universes corresponds to the first outcome, to the first die being a 6. This is the one. So the answer is 1/6. And here is what I'm trying to say again. Originally, more universes with desired outcome, but also more universes in general. The information F does affect the number of universes, but does not affect the proportion. You understand? So every information affects the number of universes, but some informations we're going to learn about independent events soon enough, they do not affect proportion. So they do not affect probability. I hope that's clear. Good. And I want to emphasize that it's incorrect to eliminate the outcome Y from consideration. What I tend to think is not that Y is not important. I tend to imagine that I know what the second die produced. So I tend to imagine that for this problem, I know that second die was a 1. So instead of imagining that information is thrown away, I imagine that I am much more knowledgeable than I really am. And that always strikes my ego or strokes my ego. Good. So we are now up to multiplication rule. And again, same thing, just to reiterate, guys. Suppose we toss two fair coins and we ask for the probability that first comes up heads. And many of you ignore the full sample space. Many of you will just say, oh, the sample space is just the outcome on the first coin, H and tail. And the probability of the first coin is 1/2. Now, the true solution would be to not ignore the sample space, but to realize, that in the original sample space, there are exactly 2 outcomes where the first coin is heads, and altogether 4 universes. So the actual answer is 2/4. It just happens to be equal to 1/2. Good. So instead of eliminating evidence, it's a good idea to imagine that you know more. Okay. So imagine when you throw fair dice, that you have a giant, almost infinite Kafka protocol listing everything else. Can you imagine that? You just toss 2 coins or 2 dice, right? So you toss here 2 coins. I imagine that here is my Kafka protocol and it's extremely long. And all the entries in the Kafka protocol are filled in except for the outcomes on the coins. Yeah, so I imagine that, so I don't imagine that everything is irrelevant. I just imagine I know everything about the universe except for the outcomes on the coins. And when I write the universes are head, tail, and whatnot, I mean everything else is omitted by default because everything else we understand. We don't need to speak about it. Do you see? This is a very important transition in thinking because it tells you to not imagine that something is not important. You imagine instead that it's given. And we're going to, in a moment, solve this question, and you'll see if you can internalize this idea. Good. Now, here is a question that will test whether or not you are if you are processing this idea. So we have 52 cards, and they're dealt equally to 4 players. Those players are East, West, North, and South. And I know that North and South together have a total of 8 spades among them. What is the probability that East has 3 of the remaining 5 spades? Okay, North and South, they have taken away 8 spades. So East and West have a total of 5 spades. And the question is, what's the probability that East has 3 spades? Can you calculate it? Well, the question is as it is, right? I will show you how to deal with it in a moment, guys. Okay, Chiara, very good. All right, guys. So here, and that's a bit surprising, maybe. We'll try to discuss why that is the right solution. So one person already offered it, Chiara did. So here is the situation, guys. So let E be the event that East has 3 spades. And look at the situation. We only know truly by the phrasing of this problem, we only know that East and West have among them 5 spades. Do you agree? Nothing more. That East and West have among them 5 spades. But what we actually assume in solving this problem is that I know the exact cards that East and West have among them. So I imagine I know the 26 cards, among them 5 are spades, and I know definitely each card, which is much more than the information provided. And if that is the case, then if for East to be successful, well, first of all, East can have any of the 26 cards. They are given randomly. So East can have any 13 out of 26 cards. And success means that he has 3 out of 5 cards that are spades, and 20 out of 21, the remaining 10. Okay. So do you understand, guys? We assume that we know way more than is actually given to us. And the way I imagine is that the event F, the event that North and South have 8 spades, the event F can be broken down into clusters of universes, and each cluster contains the same number of equally likely universes, right? So let's say each cluster contains, so a cluster will be a distribution of cards given that they have this particular 26 cards. Another cluster, all universes with a different collection of 26 cards. Right, and within each cluster, I'm hoping you can imagine it, guys. I imagine like lots of universes, and I imagine bubbles containing the same number of universes per bubble. Right, so there is lots and lots of those bubbles. Together, the bubbles make up F. Right, and we are located in one of each basically, regardless of which bubble we're located in. It's just we can always scale it down. It's basically the number of universes in F is a certain number multiplied by a particular value of bubbles, a particular number of entries in the bubble. I'm not sure if I'm losing you guys, or are you still following, right? It's a sort of thing that it's very easy in one hand and somewhat difficult to explain. I will give you lots of other examples as we go on with fewer cases, because here the number of universes in each bubble, in each particular collection of 26 cards, is just large, right? But we can just, in other words, what I'm saying is that the actual event F is equal to disjoint events F1 union F2 all the way to some Fn, where n is and each F1, F2, F3 and onwards are a particular collection of universes, right? And that is particular collection of 26 cards that are distributed among East-West, right? So the probability that East has 3 cards that are spades, this is the event E. And E can be written as E1 union E2 union all the way to En, right? Where each E1 corresponds to a particular, E1 is a subset of the cluster of universes F1 and onwards, right? They're like this. So what happens is that when I calculate number of E divided by number of F, this is the same as the number in E1 divided by number in F1. You follow how I'm thinking? Right? So E is 3 spades, but 3 spades among which 26 cards? Am I in the cluster of universes F1 or F2 or F3 or Fn? And then I have a specificity E1, E2, E3, etc. Right? And because the subcluster E is a subset of F in such a way that each subcluster in E is inside of a subcluster of F. That I mean a subcluster here. Okay, I'm hoping that this makes good sense to you. Yes, I'm very proud of what I just said, but I'm not sure. Some of you look at me confused. Like probably the review is like, "My God, this person does not make any sense whatsoever." All right. So now we come to multiplication rule. Okay, and this is, you probably took some probability in elementary school or high school, and without explanation you multiply probability. So let's say probability that the coin when tossed twice gives you 2 heads, it's 1/2 times 1/2. Why did you do that? So here is a sequence of events E1, E2, E3 in S. And we want to calculate the probability of the intersection. So the probability of the intersection will be the probability of event E1 times the probability of event E2 given E1 times the probability of event E3 given E1, E2, and onwards. Okay, that's the condition. Now we can prove this to be true very simply. We can see that we can write this telescoping product. Look at it, P of E1 multiplied by P E1 E2 over E1. And you can see I colored them, right? And the next I will just add the event E3. So it's P E1 E2 E3 divided by P E1 E2. So you can see the blues cross out, the blacks cross out, the reds cross out, and eventually there will be a green somewhere here crossing out the green here. So when I simplify, the only thing remaining is the numerator at the very end. Yes, the numerator at the very end. You should basically, when you go home, you practice that you can derive this property. It's very easy. It's a telescoping product. And then if you understood conditional probability, which of course with your intense studying, I'm sure you have. Yes, you prove this problem. So this is just probability of E1. What is this? This is the conditional probability. The conditional probability of E2 given E1. For your exam, by the way, I'm planning to write a few or include a few actuarial problems. I'm sure you want to become actuaries or some sort of thing like that. You're aware of this exam, yes? Yes. It pays a lot of money and gives you a lot of stress, I think. But it's a good application. So I'll include a few actuarial questions. Yes, apparently, right? So I don't know what the other exams are, but probability is the only thing that matters. So I'll include some questions from there. So we have this is the product. Good. Now, the next question, if you want, I might skip it. It just uses this extra, maybe I'll cover it, why not? Here we talk about, again, you remember we have these different notions of randomness. We can take a bunch of numbers, like when you play a lottery, you can imagine drawing the numbers right away, or you can imagine drawing the numbers sequentially, right? But here we are going to prove that drawing the numbers sequentially and right away is just produces equal notions of randomness using conditional probability. We did it using other ideas before. Okay, so the idea is that I'm going to, I want to know what's the probability of drawing balls 1 to all the way to n. And out of them, we want to draw k balls sequentially without replacement. And we want to show that at each step, so we know here in this problem, at each step, each of the next balls withdrawn is equally likely to be the one picked out. Right, so you see there is a slight difference between what we did before. Before we considered sequence. Each sequence is equally likely, or each unordered collection of numbers is equally likely. Now we imagine that that we have this notion of randomness. One ball is picked. Now there are fewer balls left in the ball, and the remaining ones are equally likely among themselves. So it's a conditional probability type of randomness. And we want to show that all of them are equivalent. They produce, you can just switch between the notions of randomness and produce the same probabilities. So what's the likelihood of withdrawing balls 1 through k, or any other sequence of k balls? Well, I can say that let ek be the event the kth chosen ball is ball numbered k. So then we want the probability p e1, e2, e3 all the way to ek, and by conditional probability, this is p of e1 times p of e2 given e1 and onwards. And then the first one is any one of n. The next one, well, given that I withdrew ball number e1, ball number 1, what's the likelihood I'll draw ball number 2? Well, it's 1 of n minus 1 balls. So you can see I take this product and I get 1 over it becomes the same thing as n choose k times k factorial. So any one of them is equally likely. So that means that it corresponds to every sequence of balls being equally likely. I just chose the sequence 1 through k just because it's convenient to label it. But obviously, I can just relabel it, and any other sequence will have the same probability, right? Which means that this notion is the same as taking any sequence, meaning that any sequence is equally likely. I hope you understand the minute differences between each statement and that they are equivalent. Right. Well, are you ready for a very hard problem? So that was the matching problem. Do you remember the matching problem? And that was gentlemen with hats. And we solved that problem under the assumption that no gentleman picks his own hat. Yes? And you remember what we obtained? If you have enough gentlemen, the probability that no gentleman picks his own hat is approximately 1 over e. The more the merrier. You can actually investigate how fast it converges. So how many people do you have to have for this to be true? So we now want to figure out the probability that exactly k gentlemen pick their own hat. Right, so we are allowing maybe 1 gentleman to pick his own hat, or 2 or 3 or 4. What happens if k gentlemen pick their own hat? So this can be described as follows. So let ej be the event that gentleman number j picks his own hat. Now the desired probability that exactly k of them pick their own hat can be written like this. Can be written as, well, by symmetry, there's how many possibilities? There are n choose k possibilities for the particular choice of gentlemen. And by symmetry, because it doesn't matter which gentlemen do that, the probability is the same as n choose k times the probability where the first n minus k do not pick their hat and the last k pick their hat. You see, I underlined in blue. So that is how you describe it, right? So it's E1 complement, E2 complement, and onwards. Agreed? So far, clear. You see, I of course did not give you too much time to think of the problem yourself, because that would take maybe an hour, maybe 2, maybe much longer. But ideally, you practice at home, because you see, 2 things that you want to learn is efficient representation by set notation. It can be very difficult sometimes. That's what we're doing now, and combinatorics, as we did before. Maybe Kafka protocol if you do it my way. So what is this, guys? I can use condition. I can condition on well, what it is. I imagine that blue is one piece and the red is another piece. It's like 2 sets. So that by the multiplication rule, it's probability of those events times the probability of the complements given that those events occurred. Yes. Now, why is it nice to do it this way, guys? Because, well, this probability, the second product, the second term of the product that I'm circling, It's the same as what we saw before. It's the same as we now removed those gentlemen, and it's like a smaller quantity of gentlemen not being able to pick their own hats. And we already know that the probability should approach to 1 over E. Agreed? If n is large, k is still a fixed number, that would still approach 1 over E, as you can imagine. And here this is the actual formula. You can review how we obtained it from the previous chapter, that was difficult, but we solved it. So the second part, here is the formula for it. Yes, this is the formula that you get if you understand inclusion, exclusion, right? Or your probability of union is, whatever it is. So that's the formula you'll get. It's a bit challenging, but hopefully you understand why, if you know that solution, you don't need to do extra work. It's the same problem with just n minus k rather than n individual. So it's this summation. Now, what about this? What about this probability, right? So we have the gentlemen picking their own hats here, and the rest can do whatever they want, right? So that means gentleman 1, gentleman 2, gentleman n minus k can do whatever they want. And so, so in the numerator, I have to have n. First gentleman n is matched with hat number n minus 1 is matched with hat number n minus 1. So altogether I have n minus k permutations for what gentlemen 1 through n minus k are allowed to do. You following me, guys? So that's the numerator here, and the denominator is, of course, I just consider all possible permutations on n people, right? They can do in general. You can create a Kafka protocol that indicates who picked which hat by writing gentleman 1 and hat gentleman 2 and the hat number that you picked. So it's n factorial permutations. That's what we get. Yes. And then when we expand this thing, I can take this numbers and simplify, and what I obtain 1 over k factorial. So that means that the probability that exactly k people pick their own hats is 1 over k factorial e to the power of minus 1. Once we go to chapter 4, you will recognize that this is very special and happens very frequently. It's known as a Poisson random variable. So there's going to be a very interesting random variable that is very useful because it's very closely related to situations where you have lots of trials, and each trial is either success or failure, but they don't have to be necessarily independent, right? So it's very closely related to binomial distribution. You will see it later. So that occurs all the time, and of course the summation you must know better than your favorite poem. Okay. Any questions? You understand how to practice this, yes? You know where to find my notes. You're aware they are on my website, yes? Good. Moving on. So now, and guys, before I do move on, I mean, I do hope that you understand how multiplication works. I mean, you just learned it this second, but do you have a sense of how to use it, right? So multiplication is always using conditional probability. You're just conditioning the events, and that results by the telescoping product that clearly results in multiplication there. So here we now consider Bayes' formula. Bayes' formula, we now have that E is equal to E intersect S, which is E intersect F union F complement, this thing. Which is equal to EF union EF complement. Good, that's obvious, right? S can be always written as a disjoint union of things that satisfy property F and things that do not satisfy property F. So E can be then broken into E and F, or E and not F, and those are disjoint. And so the probability of E is the sum of the disjoint probabilities. And here I can use conditions. So that means what is probability P and F? It's the same as the probability of F times probability E given F. I wrote it just in other order, but it's really that same multiplication formula. Yes. And what's the second part? It's the probability of E given F complement times probability F complement. Are you with me, guys? You just have to train yourself to very quickly convert this event, right? So probability of A given B is probability AB divided by probability B, yes? Which means that probability A given B times probability B is always the intersection. Right? It's the multiplication formula for two elements. Very easy to remember it this way. And of course, it's easy to extend it in general. All right, so here is, and then of course, you know, this is just 1 over P probability of F complement is 1 minus probability F. So here is the first question. So insurance company divides people into two classes, accident prone and not accident prone. Statistics show that an accident prone person will have an accident within a year of with probability 0.4. Whereas this probability is just 0.2 for a non-accident prone individual. And we know that 30% of the population is accident prone. What is the probability that a new policy holder will suffer an accident within a year of getting the policy? You understand? So the insurance company wants to understand how likely is this new person that we don't know to have an accident. And of course, that depends on whether the person is accident prone or not, right? So that's why we consider it. And rather, we just want the probability that a person will have an accident. If somebody signs up for the insurance, what's the probability of an accident? All right, so it's a sort of way between how likely the person is accident prone or not, right? All right, Gustavo, well, looks believable. Nicholas, I'm not following exactly. for accident prone, the probability is 0.4, I think, right? 0.4. And 0.2 for non-accident prone. Okay, Chiara, looks reasonable. Okay. Thank you. Thank you, Nicholas. One thing I don't know is arithmetics. All right, so let's solve it together, okay? So let A be the event policy holder has an accident in a year or within a year, and I be the event the person is inclined to have accidents, okay? That's how I set it up. So I want the probability of accident. So that clearly I can condition by accident and being inclined, and accident and not being inclined. Yeah, so I skipped here a step just to be sure. Let me write that step here, just if it helps. So probability of accident is clearly the same as probability of accident and inclined to have accidents, like me, and accident and not inclined to have accidents. Yes. And this is disjoint, so they can be written as probability accident and inclined plus probability accident and not inclined. And then I can, those are intersections, I can condition them, right? It's easy to evaluate likelihood of accident if the person is inclined based on the information. So I just write probability of being inclined times the probability of accident given that the person is inclined plus probability of not being inclined times the probability of accident given not inclined. Yes. So what is the probability of being inclined? That's 0.4. Probability of accident, if that happens, probability of being inclined is 0.3, correct? It's 0.3. And probability of having an accident is 0.4 plus accident and the probability of not being inclined is clearly 0.7. If 30% are inclined, the rest are not inclined. Times 0.2. And the result is 0.26. Yes? So you understand the logic, yes, guys? What I did is I just considered intersection, and in this situation, it's easy to evaluate probabilities relative to a situation. So for the population of accident-prone people separately, and then this is a sort of weighted average between them. Where did I get 0.2, Barry? Well, 0.2 is the probability of an accident given that the person is a good driver, maybe, if that's the situation, right? So if a person is a good driver, according to this question, the accident will happen in a year with 20%. I don't know in which country, but 20%, it's pretty high. Good. Now, next example. New policy holder has an accident within a year of getting this policy. What's the probability that the individual is accident prone? So you understand what happens now, guys. Now I know the person had an accident. Now I need to classify how likely is this person to be accident prone? Solve this, please. What's going on, guys? Stuck? Well then. So this is the question. So we know the person had an accident, right? How likely is the person to be accident prone? You would agree that just when something happens, that indicates, you see, when somebody has an accident, you already suspect maybe the person will have it again, correct? So right away, when somebody instinctively you do that, right? Also, if somebody steals once from you, you do expect that the person is prone to stealing, right? So it's a similar thing. It's a bias that you naturally have. So let's see what's the correct probabilistic bias that we should have that this person will have another accident. So this is the situation. That's what we are evaluating. Agreed? We know that this is what happened, an accident, and I want to know how likely the person is to be inclined to have accidents. So by conditional probability, this is the same as probability of accident prone and accident divided by probability of accident. Yes, we calculated the probability of the accident already in the previous problem. We know it's 0.26, the probability of just having an accident without any qualifications. Now this probability is best tackled with conditional, with the conditional, and that would be just probability of being accident prone times the probability of having an accident given accident prone. You see, in the numerator, I reversed what happened and I reversed what you call posterior and a priori probabilities. Prior and posterior probabilities, right? Here, the prior probability was A and the posterior was of I. Here, the event, the prior event is I and posterior event is A. So we have that numerator, it's what? It's the same as probability of accident given accident prone is 0.4, probability of being accident prone is 0.3, so it's just 6 out of 13 or approximately 0.46. So it's more likely the person is accident prone than just a general person from the population. You follow? Here is another question. Well, before I go there, right, it's a question about multiple choice, your favorite. Do you know what Russians call multiple choice questions? American. So multiple choice question exam is an American exam. So here is that situation. So suppose, guys, that I ask you a question that, before it was determined that the probability that a person knows it is P. You can determine by doing statistics. In other words, I ask this question and I see how many people know it, right? And let's say I asked it out of, let's say, 100 people and 10 of them knew the answer. So then I assume the probability is somewhat around 10% or 0.1, right? So I know the probability from statistics that it's P. And the multiple choices are M. They're M multiple choices, right? So let's assume that the probability, so let's assume that when a person knows the question, he always answered it correctly. It's not always true. Sometimes you mistype or accidentally select something, right? So we simplify and say, let's assume that the person always answers the question correctly if the person knows the answer. Are you with me? And other than that, if the person doesn't know, let's assume the person is just guessing. So the probability of successfully guessing is 1 over m, because there are m choices. You agree? And each choice is equally likely to be the right answer. Okay, so given that the question was answered correctly, what's the probability student knew the answer? You understand? Because it could be that the person guessed it, it could be that the person answered it correctly, correct? So calculate. All right, Gustavo, that's good. Okay, Nicholas, looks nice. All right, let's do it together, guys. So an important skill is just labeling correctly what we want to examine. So K is the event student knows the right answer, right? What's the probability of K? We know it's P, right? Whatever that P is estimated from statistics. And C is the event student answers this question correctly. And what we want to know is the probability that the person knows, given that the answer is correct. And then just working it up, it's the probability of correct and the person knows the answer divided by probability of correct. Now, numerator, I can just simply, it's two events. I can condition probability of knowing, probability of correct giving knowing. Now, probability of correct giving knowing is, given that the answer is known, is 1. And probability of correct is P. Yes? And the denominator, probability correct, is, it can be broken into correct and knows and correct and not knows. Yes? And then you have this denominator. I hope you understand how to get the denominator. You agree? Practice it, guys. Make sure you practice it. So what is this? This part is the same. and the second part is 1 over m times 1 minus p. Good? So this ratio can be also written as mp divided by 1 plus m minus 1p. Just you can simplify it, multiply everything by m, and that will simplify to the situation. For instance, if we know that 10% of the student population knows the answer to a given problem, and there are 5 multiple choice questions, the probability that the person knows the answer, given that the answer is correct, is just 36%. So it's actually low, you see. So for this given question, if there are five choices, a person can guess it, as you can imagine. Right, so it might be just slightly more than a guess. If the person was just merely guessing, it would be 25%, and the actual probability is, of the person not guessing is not that much higher. You agree? All right, guys. So the next question, if you want, I'll show you what it was inspired by. So if you go to Russia, you know, you can go and pet lines just for an extra fee, no problem. I can show you where, if you want to go to a place where you'll get to pet lots of lines. Would you like to see that? No? Okay, some people say yes. Let me quickly show you.
Is located in Crimea, Russia. There are about 80 lions at the safari park, making it the biggest lion park in Europe. But there are also approximately 1,500 other animals and birds at the park.
Here is the essence what you need to know what you can do. You just go there and...
Конечно.
Yes.
Что ж вы сзади там, жена?
Good. So you now know where to go, correct? If you ever need to pet lions, you just cannot live without it, just go there. So an autistic savant wishes to pet a lion in a Russian zoo. Yes, but the bears, I mean, in this particular park, I looked at documentaries, I examined this guy who runs it. I think it's the largest ever gulag for bears. They are sitting in prison, serving life, pretty horrible. You know, Russia is a place of bears, you know what happens. And 1/3 of them sit there behind bars. So the savant cannot tell a bad lion from a good lion, but knows that the bad lion bites with probability 0.9, whereas the good lion bites with probability 0.4. If the savant gets mauled by a lion, what's the probability that he went to pet the bad lion? Here is lion bad and lion bad complement. Good. Go ahead and calculate the probability. Where in Russia? I mean, they're just a choice between two in this case, but in the problem, there is just this and the other guy. Okay, guys, you see what happens. If you pet this one, the likelihood you will bite is 0.9. You pet this one, the likelihood you will bite is 0.4. If the guy was, if the savant was attacked by a lion, what's the probability it was a bad one? All right, Gustavo, looks reasonable. Oh, be careful. Let's say not quite, right? Here is the thing. the person was attacked by a lion. Given that information, what's the probability that it was the bad lion that did it? All right, Nicholas, not bad. I mean, looks believable to me. So here is the situation, guys. So M is the event that the savant was attacked by the lion, and B is the probability that it was the bad lion. Okay, what's the probability that it was the bad lion given that there was an attack? So it's probability of attack and a bad lion divided by probability of attack. And then I can condition the numerator. It's the probability of bad lion times the probability of attack given bad lion. You agree? You see what I do, guys? Once I have the intersection, I can decide, do I want to condition on M first, or do I want to condition on B first? And that's easier to condition on B. Agreed? So we have this situation, and the denominator I write attacked by bad and attacked by good lion. And then I condition each of those. And because the savant, here is the important part here, guys. The savant cannot tell the difference between a good or a bad lion, which means the savant is equally likely to pet either the good lion or the bad lion, which means the probability of touching the bad lion or the good lion is 1/2. And by that, it's 9/13, or approximately 69% that the attack was perpetrated by the bad lion. Understood? Okay. Make sense? So you see, guys, I do hope you will practice this skill. You have to come up with letters. You have to do this Bayesian thing. And it's not as hard as it looks. And if you want slower practice, of course, you can stay after class. I will help you in office hours. All right, so here is another interesting question, very interesting in light of the past 2 years. So Vasya is tested for a disease that afflicts 1% of the population. The test result is positive. Assuming that this test is 95% reliable, what is the probability that Vasya is afflicted with the illness? So let me explain to you what 95% reliability means. Let's simplify this. We are not distinguishing between sensitivity and specificity. So the idea is that 95% of the time, this test will correctly say the person has the disease, given that the person has it, you see? So if the person has the disease, out of 100 people that have the disease, 95 will be correctly identified as having the disease. And conversely, out of 100 people that don't have the disease, 95% or 95 people will be correctly identified as not having the disease, you see? So the probability of a false positive is 5%. And the probability of false negative is also 5%. Understood what I mean, guys? So it's always given, right? So 95, let's say it's the same in both directions. So what's the probability that the Vasya has the disease given this information, that he tests positive? And of course, for yourself, simplify it, guys, and we'll do it in two ways. Okay, so here D is the event that Vasya has the disease, and T is the event test is positive. Okay, so the probability of disease given test is positive is it's the same as test positive given disease, probability of disease, divided by test positive given disease, probability of disease, plus probability test positive given no disease, probability of disease, which gives you this number. Okay, so test positive given disease, 95%, right? And the probability that the person has the disease in general is 1%. Now here, test positive given no disease, that's a false positive. False positives will be 5%. So it's 0.05. Probability of not having the disease is 99%. So altogether that reduces to 16% likelihood. So the person is only 16% likely to have the disease, still rather low. Of course, you do notice it used to be 1%, now it's 16. So it's 16 times more likely than before the test, but it's not very certain. A lot of people think that a test like this is very certain, but it's tremendously not. Right? It's much more likely the person does not have the disease. Good. Now, why is this probability so low? Here is a diagram that might help you understand what's going on. So suppose we have 10,000 people. Good. 10,000 people. And out of them, how many are going to be diseased? 100, correct? Because it's 1%. And the remaining are healthy. You see, so those two numbers, they add up. Yes. Now, if I test those people, some of them, so 95 will be correctly identified as having, well, 95 will be tested positive, right? And that's that's the true positives. And 5 will be false negatives, yes? Now, of the healthy people, 5% will be tested positive. Do you agree? That's the test positive is 5%, so it's this number, and negative will the rest, right? So you see, we have this number is fairly large, so it's 95 divided by the sum of 95 and 490. So basically, if you test positive, if you given that the test is positive, you are either in this, you are either among the 95 true diseased people or among the 495 false positives. So it's this number divided by true positive plus 5 positive, which is this, you see? And because this number is very large, the ratio is actually still in favor of you not having the disease. The test had many opportunities to be wrong. That's the point, right? It might be good, but it had way too many opportunities to be wrong, so that generates a huge number. It's like 1% out of a million is much better than 200% out of $5. You see, similar thing, right? So although the being positive here is not likely, you have lots of people for whom it can happen. Good. Now, the next question, guys, let's see if you can solve this one. Now, Vasya decides to test himself again. And again, the test is positive, and it's independently of the previous result. So again, the test is positive. What's the likelihood that Vasya now has the disease? He goes for the second test after this one. And again, it's positive. Here is the best way to solve this problem, guys, right? So we have 95. If we continue from this drawing, we can actually do it again using set notation, but we can use this drawing, right? So 95 and 495 are the first test positive. So Vasya belongs after first test either in this box or that box. Now, if he tests positive again, he belongs, if he's in the true positive, again, out of 95 people, 95% will be tested correctly positive. So he'll be part of this group. Out of 495, if he belongs in that group, to be tested positive, only 5% will be tested positive, yes? So now, Vasya, if he has the disease, he is, this is the number, he is in this number, divided by the total of this plus that, which is about 78%. So now the probability that Vasya has the disease is 78%, if the second test is also positive, independently of the previous one. Yes? Make sense? You can solve it using letters. I think this drawing is, in this particular case, slightly easier. You don't understand, you realize, because you realize what's actually happening, correct? You realize what happens. What happens, you're narrowing down into which universe you belong to, right? The universe of doubly positive tested people, those are the incorrectly doubly tested people and correctly doubly tested people. And you just select one of those universes. Good? All right, so I suppose the next question is we'll tackle next time, maybe on Monday. All right, guys, thank you for staying. I do hope you understand. I'm sorry if I move very fast. I told you that material is just way more than can be covered in the semester, and I try to leave time for the material at the end, right? Integration and all that stuff, which I barely get to usually once online classes started. So try to stay on top of things and try to understand it really well. I really would be happy if you come up from this class and know something. Take care.